Welcome back. So, impacts are going to happen. How can we minimize the hazard that space presents to us? Well, there's a number of things we can do. First, we got to identify those threats in outer space. Once detected, we can blow it up in space. I know, sounds like a movie. But small pieces could become radioactive, rain down on Earth. Bad news. Again, sounds like a movie because it was. We can try nudging it out of Earth's orbit. We know it's coming this way. Instead of blowing it up, can we just push it out of the way? Again, sounds like a movie. Technology that we're working on, in fact, on some missions, can change the orbit of an asteroid. We can evacuate. I don't know how well that would work, depending if it's big or small. It's possible if we can predict a precise impact point with computer modeling and physics. We can actually do a pretty good job of that. But obviously, evacuation is kind of out of the question. If it's a large impact, there's really no safe spot. So again, if some of these things sound like movies because they were, Armageddon, they blew them up. They blew a spoiler alert. Armageddon, they blew up an asteroid with a nuclear bomb. Probably not the best idea. Deep Impact, they tried to do the same and nudge it out of the way. It didn't really work. Armageddon, happy ending. Deep Impact, maybe not so happy ending. Spoiler alert. So there are defensive strategies we can take for impact. So very recently in 2005, Congress directed NASA to evaluate the dangers asteroids present to Earth and to report on methods to survey for dangerous asteroids, how they can look for them, and ways to divert those on a course for Earth. This directive created ATLAS, the Asteroid Terrestrial Impact Last Alert System. Government loves their acronyms. So the purpose of this was by 2020, so a couple of years back, it ought to be possible to find at least 90% of asteroids with a diameter of 500 feet or larger that come close to Earth. So that was the goal, and they're letting slide 10% evidently. So 90%, that's a good amount of things 500 feet or bigger. And something of that size could have some drastic effects, more locally, but the bigger it gets, obviously, the more catastrophic. So it was developed in coordination between the University of Hawaii and NASA. It consists of actually two telescopes 100 miles apart, which automatically scan the whole sky several times every night looking for moving objects. And the reason they use two telescopes is just the same reason why two eyes are more easy to focus on things than just one eye. So it's binocular vision, two sets of telescopes kind of looking in the same area, because you get much more sense of movement with two eyes versus one. Same thing with telescopes. So Atlas will provide 1 day's warning for a 30 kiloton. That's the amount of explosive energy some of these impacts would have. A small town killer. So, a small town, let's say like Flagstaff or something. An asteroid or meteorite of small enough size that would destroy, for instance, a small town like Flagstaff, they would get a day's warning. For a 5 megaton large city killer like Phoenix, something that large, we'd probably get a week's notice. For a county killer, something that would just destroy all of Maricopa County, a 100 megaton event, we would get 3 weeks warning. The bigger the energy, it means the bigger the asteroid. It means that's the easier it is to see out in space. Again, just for a reference, the Hiroshima atomic bomb was a 15 kiloton explosion. So 100 megatons is 10,000 times bigger than Hiroshima atomic bomb. So we're talking a lot of energy. So again, these two telescopes are kind of in the state of Hawaii, one on the island of Hawaii and the other, I believe, on the island of Maui. I'm pretty sure. This is the big island of Hawaii. I believe this is Maui. The reason these places were chosen were it's kind of out in a dark area on the middle of the ocean, on some relatively high peaks with a lot of clear weather. So that's why these sites were chosen. And this is one of those. And again, you got these two telescopes kind of looking in the same area, but they can scan the whole sky several times per night, and they're looking for moving stuff, which is easier to see with two eyes versus just one. Under favorable circumstances, under the perfect circumstances, Atlas can detect a 100-meter diameter asteroid, which is relatively small. That's a soccer field, 40 million kilometers away. That's a quarter distance to the sun. So it can find something pretty small, 40 million kilometers away. Even smaller than that, so 10 meters in diameter, so, about as big as a house, maybe a small little house. It can detect that about 4 million kilometers away, which is about 10 times the distance to the moon. So we can still find little things pretty far. So far, Atlas has discovered 437 of those near-Earth asteroids and 45 potential hazardous asteroids, on top of what we already knew. So great, we can detect them. How do we stop them? Well, enter something, for example, called DART. This is the Double Asteroid Redirection Test. Again, government loves their acronyms. This is a mission, because it's currently in action. This is a mission to see if a spacecraft could impact, so the spacecraft running into an asteroid has enough momentum, mass, and velocity to hit this large asteroid to even deflect it just a little bit. So if we have something large coming, can we throw a big satellite at it, a little spacecraft at it, and hit it, nudge it just enough so that instead of coming towards Earth, we just hit it just enough and it just kind of slightly nudges it out of the way. That's the whole goal of this thing. So DART is an impactor. It hosts no scientific measurements other than a sun sensor and a star tracker and a camera, all to help navigate. Other than that, the whole goal of this thing is just to smash this thing into an asteroid. And then we'll use some ground-based telescopes and other satellites out in space to look at the trajectory to see if it's changed. So it's a pretty heavy little spacecraft, and it will produce a velocity change in the asteroid of only 0.4 millimeters per second, which is a small change in speed and a small change in direction. But over a long distance, even though it's just a small little change in direction, over time, over that long distance, that small change in direction would mean enough moved out of the way to where it wouldn't really hit Earth and shift it out of the path of Earth. So this is just a test. And they're targeting Didymos B, which is a 535-foot diameter asteroid. Now, this asteroid isn't, don't worry, it's not currently on the way to Earth. So that's why they're doing this. They're testing an asteroid that's not in the direction of Earth, and hopefully when they hit it, they redirect it not at Earth. So that's why they chose Didymos B. Overall, again, it's expected to alter the speed and direction very, very fractionally. And again, Didymos is not currently an Earth-crossing asteroid, so there's no possibility the deflection will knock it in the direction of us. And the launch date was actually not too long ago. Due to COVID, there were some delays, so it was actually launched November 23rd of 2021, and it's expecting to impact September 30th. So that was the last time I kind of looked this up. Things, some subtle dates may have changed, but, this is all underway. So Didymos is actually, there's an A and a B, and so it's kind of like a dual orbiting asteroid. And so we're sending this spacecraft essentially just to smack into this thing to see how it deflects. Okay, so we can detect them. We can deflect them. So who oversees all this stuff? Some secret agencies? Is it NASA? Well, not secret necessarily, and it's actually not NASA. So we have the Planetary Defense Coordination Office, So this office ensures the early detection of PHOs, potentially hazardous objects, those that orbit within 5 million miles of Earth, and that have a diameter of 30 to 50 meters or greater. So this office tracks and characterizes all of these PHOs, issues warnings, which they've never really had to, of the possible effects of the impacts. They study strategies, technologies for mitigating all of these PHO impacts. And they do play a leading role in coordinating the U.S. government planning for response to an actual impact threat. So this office plans and thinks about these things. That's their little logo there. So it was established in 2016. And what this graph over here shows is the time of discovery of asteroids in relation to their closest approach, the closest they would ever get to Earth. So recently, of all the percentage-wise of asteroids we have detected versus when they would come closest to us, what's our percentage? So actually, 60%, over 60% of asteroids that this office has detected, we've detected after they've already had their closest approach to Earth. So a little late to the game. 13% less than 24 hours before their closest approach. Again, none of these obviously hit Earth. Up to a week, so 24% more than a week, and then kind of drops off from there. So asteroid discoveries by count. So where are these telescopes that discover them? Well, here's the Atlas ones, and I forget when this data was taken. So here's the Atlas one. So I think the current data of all this stuff is from a few years ago, the most current I could find. But a lot of them are found from the Mount Lemmon survey, which is Mount Lemmon, just outside of Tucson. The University of Arizona does a great deal of research with telescopes. They actually made the James Webb Space Telescope, the most recent one that we launched into space. So the University of Arizona is amazing with telescopes and planetary science and space science. So the Mount Lemmon survey is a bunch of smaller telescopes, and they have discovered a good number of asteroids. And so that's just outside of Tucson there. In coordination, again, with the University of Arizona is the Catalina Sky Survey. Sorry, I'm going to move me again. It's a NASA-funded project supported by the Near-Earth Object Observation Program under the PDCO, based at U of A's Lunar and Planetary Lab in Tucson. Its mission is to discover more of these NEOs, to try and meet that congressional mandate to catalog at least 90% of the estimated NEOs larger than 140 meters, some of which would be classified eventually as PHOs, in addition to identifying impact risk. So I was looking most recently, when I made this video in kind of late March, kind of the stuff that's closest to us, and I noticed a couple of asteroids of decent size that are coming pretty close to us, moving at a distant speed. And so that's 2010 GD35. So here's Earth. Here's where that is. So that's the orbit as of March 29th. And Earth is here, and 2022 EK1 is here. So we can, you can find this information. You can find where these things are. You can see how their path brings them within a trajectory of Earth, classifying these as near-Earth objects or even potentially hazardous objects. So we're detecting them. We're thinking about how to deflect them. We have offices coordinating all of these things. So we're actively thinking about this stuff. So a lot to digest there. Let's go ahead and pause. When we come back, we'll talk about meteorites and impact events in Arizona. Bring a little home state flavor to this. See you back here in just a second.